Okay, so in the last video, we did some work with geometry and linear transformations, and we got reflections and dilations and this thing that's called a shear, which is kind of a slide, but it's not exactly a slide, but still similar in idea. And today we're going to kind of talk about rotations. So in each of these, we're going to have T being a linear transformation that eats some vector that is going to be represented by a matrix eating that vector. And that vector is living in R3. So that means the A matrix is going to be a 3 by 3 matrix. Okay? So what we're going to do here is we're going to give you three matrices. One that will produce a counterclockwise rotation around the z-axis, one that will produce a counterclockwise rotation around the x-axis, and one that will produce a counterclockwise rotation around the y-axis. Now, here's the deal here. The reason why counterclockwise is that we're again thinking in terms of a right-handed system. So this is the mathematical system that we use. Also, we did do something like this in R2. If you remember when we were playing with conic sections and rotating them so that you could do change of basis and end up with being able to complete the square to get the conic section in standard form. It's the same rotational matrix here, but it's going to be in a three-dimensional version. So the rotational matrix that will work for the z-axis in the counterclockwise direction is as follows. You basically create that cosine sine matrix up in the upper left-hand corner here. So you get cosine theta minus sine theta, sine theta, cosine theta. So that's going to give me the rotation, but I'm going to fix z. So anything that's on the z-axis is going to stay put. And this is why I get the zeros and the 1 at the z spot. The x-axis works the same way. Instead of having the rotational matrix in the upper left-hand corner, it's now going to move to the lower right-hand corner. So I get the 1 is now up here with zeros going across and zeros going down. This is cosine theta negative sine theta, sine theta, cosine theta. So this will give me the 1 for rotation around the x-axis. The weird one is actually the y-axis one. Okay, so kind of thinking this through, the split for the 1 is logically going to be in the middle. So the middle term is going to be a 1. We're going to get zeros in every direction from that. That should be expected. What is unexpected here is where the negative sign ends up. So you have a cosine theta here and a cosine theta here. That's expected. However, the negative sine theta is down here, whereas the positive sine theta is up here. So these will all produce counterclockwise rotation of theta degrees. You can also imagine it as theta radians around the given axis. So take a point, make that point a vector, x, y, z, have A eat that vector, and then you'll get, and let's call it x prime, y prime, z prime, that is rotated theta degrees around the given axis. All right, so there you go. This is rotation around axes using linear transformations. Awesome.